So our third skill in our sixth learning unit on thermochemistry is about enthalpy. Remember, enthalpy is delta H and Hess's Law. So just kind of bringing in some content that we've learned from our previous skills. Remember, we talked about how we can determine delta H, which is really the heat given off or taken in by a system. We can use experimental methods. We can use calorimetry. And our equation here, remembering that delta H will be equal to Q. So using our heat capacity equation that we learned in our last skill, we can actually determine delta H experimentally. So the next two skills are actually teaching us how we can determine delta H for a reaction in other ways. So we can also, using something called Hess's Law, determine delta H empirically. So empirically means doing it via calculations. Experimentally obviously means doing an experiment in the lab. So we can determine delta H empirically using Hess's Law. So here's what Hess's Law is. Hess's Law pretty much states that the enthalpy change of an overall process is going to be the sum of the enthalpy changes of individual steps. So the delta H for an overall process will be the delta H for individual steps. So what do we really mean by individual steps? Well, we're actually meaning individual chemical reactions. So what we're going to see here is we're going to have a set of equations. Each equation will have its own delta H value, and we need to figure out how do we flip or change or manipulate these equations. Remember our first skill, we sort of talked about two ways that you can manipulate thermochemical equations. You can flip them and change the sign, or you can scale them and change the magnitude of your delta H values. So we're going to put that into practice here. So we're going to rearrange, sum, and manipulate thermochemical equations to give us our final overall equation. So a couple of bookkeeping things to think about here, and then we'll go through one example, right? The first thing we want to think about is identifying what your target equation is. Maybe it's something that is provided for you. Maybe it's something you need to take chemical names and make them into a balanced chemical equation. But again, we're going to have an equation whose delta H is unknown. We want to make sure that we take into account the amount of each reactant and product. And when we go through a couple of examples in class, we'll talk a little bit more about what we mean by that. And then we're going to manipulate given equations with known delta H values so that we can sum these up and then have our overall target equation. So those two things that I just talked about, skills that we learned or concepts that we learned in skill 6.1, were how we can change the sign of delta H if we reverse a reaction. We'll talk about that as flipping a reaction. Or we can scale up or down a reaction. We talk about changing the magnitude of that. So we'll talk about scaling and flipping. And you'll see that when we do an example here. Third step then is that you add all of these manipulated equations together. We're going to add their delta H values. So this is going to be an important thing to think about. We sum equations and we sum delta H values. Okay, anything that is present on opposite sides of an equation can cancel. So again, we'll see that in our example that we have here. So we're just going to do one quick example here. We'll have lots of examples that we'll practice in class, but this is a little bit of a simpler skill to think about here. So little context here for our chemical equation. Two pollutants that form in auto exhaust are carbon monoxide and then NO. So we've got an environmental chemist that wants to convert these pollutants into less harmful gases, carbon dioxide and nitrogen gas, as follows. So they give us a chemical equation here, and we want to determine the delta H for this reaction. So something to keep in mind. Remember in our first skill for this learning unit, we talked about don't be scared of fractions. That's okay. Sometimes we're going to see equations that have fractions, but that's important because the delta H that we're going to determine is going to be contextualized by these fractions. So it's important that those fractions are there because our delta H is going to be corresponding to those specific ratios of quantities. All right, so here's the information that's given. I'm going to walk through how we sort of think about this problem and what you want to think about doing. So I'm going to look at my equation that I want to get to, and then I'm going to compare the equations that I'm given. And the first question I'm going to ask is, are things present on the correct sides? So let's take our first equation here. I've got carbon monoxide on the left. I want carbon monoxide on the left in my overall equation. So this one looks like it's set up to be in the right direction. Okay, I'm noticing that I have oxygen here, but I don't see oxygen in my equation. So this probably is going to be something I want to cancel out. And then I've got CO2. So CO2 here, yep, that's on the right side. Correct, as well as on the right, the product side. So those guys that I've identified in green there are in the correct positions already. Let's look at my next equation here. All right, NO. Oh, I want NO on my reactant side, but the equation that I'm given here has NO on the right. So this is a little bit of information here that tells me I need to flip this equation. So this is going to be flipped. Let's see if other things work here to flip. Yep, look at this. I need to have nitrogen as a product. This one has it as a reactant. So definitely want to flip. And look here, when I have this oxygen here, when I flip this, I'm going to have oxygen over on the right. And that's going to be important because then it can help cancel out my equation A that has oxygen on the left. All right, so something else that I'm noticing here, I can see that these coefficients here don't match. I have a 1 and that's a half. I have a 1 and that's a 2. So I need to scale this equation. And so I'm going to scale this by multiplying by 1/2 x. So hopefully conceptually that makes sense for you guys. The next step is I'm actually going to write these equations and then we'll sum them up. So my first one, I'm just going to say that there's no change here. I'm going to use this guy as is. So CO gas plus 1/2 O2 gas goes to CO2 gas. My delta H for that reaction comes over just as is. I haven't manipulated that. Okay, that's the first equation. Now the second equation, I got two things that I have to do with it. Let me treat the equation first, and the same thing that we do to the equation, we have to do to the delta H value. So the equation, I need to flip it and then scale the coefficients down by 1/2. So flipping it means my NO comes here, and I'm scaling the coefficients down by 2, by half, and so that's only going to be a 1 there. There's only one product that now becomes a reactant, and now I'm going to scale these other guys down as well. Okay? So I've scaled everything down, and I flipped it. So how you need to manipulate the delta H value is you need to scale that down by half, and because we flipped the equation, we changed the sign. So this is now going to become, it was positive 180.6, now it's going to become negative 90.3 kilojoules. Okay? So the same thing that we needed to do to our equation here, we needed to do to the delta H value. Okay? So this flipping part is why that's now a negative. This changing by 1/2 is why this is now half of what it was. So the last part to work here is just to add up our equations. Okay? Remembering anything that appears on both sides of the equation we can cancel. So I've got 1/2 O2 on each side, so I can cancel that out. And I'm going to keep everything that was a reactant still being a reactant, so CO gas plus NO gas. And everything that's a product stays as a product. CO2 gas plus 1/2 N2 gas. The delta H for this new reaction is going to be the sum of delta H for the first reaction plus delta H for the second reaction, and then ends up being minus 373.3 kilojoules. So that's how we do Hess's Law. You'll know you'll have a Hess's Law type problem because you're going to be asked to figure out delta H for a reaction that you don't know, and you're going to be given equations with delta H values that you do know. So that's how you'll know you'll have a Hess's Law problem. You'll have a bunch of equations that you need to manipulate to add up to your overall equation. As we'll see when we start doing some problems in class, sometimes there's more than one way to get delta H for a reaction. We're going to see one final way in our fourth skill.